Today we're on page 2 of the Chapter 14 AP Chemistry packet, and we're going to talk a little more in detail about pH and H+, and how to fill in a chart like this for all the missing values. Let's review briefly the relationships we talked about on the last page, where we learned that Kw is equal to the concentration of H+ times the concentration of OH-. At 25 degrees, this is going to be 10 to the minus 14th. So let me just add this in briefly so we remember that this is only at 25 degrees, which I did write actually over here, but just want to remind you that it's always going to be at 25 degrees for this 10 to the minus 14th. If you change the temperature, this number is going to change, but most of the time we're going to be at 25, which is the room temperature. Okay, we learned before that the pH is the exponent after the negative sign of the 10 for the concentration of H+. The same could be said for the concentration of OH-. We learned that to get the pH, you could take the negative log of H+, and of course, to get the pOH, you could take the negative log of OH-. And then you can also see the relationship between pH and pOH, that they add up to 14 up here. And of course, H and OH multiply, like I said, to give you 10 to the minus 14th. So let's start with water. We know water is neutral. So if it's neutral, it has the same amount of H+ and OH-. If you have more H+, you're an acid. If you have more OH-, you're a base. So since these are the same, these numbers have to be the same. And what times itself gives you 10 to the minus 14th? That's going to be the square root of 10 to the minus 14th, which is 10 to the minus 7th. So this is going to be 10 to the minus 7th. Now technically with Sig Figs, you'd want to write 1.0 times 10 to the minus 7th, and here you would write 1.0 times 10 to the minus 7th. Now if you wanted to find out the pH of this, you could take the negative log of H+. So if you take your calculator, and you might want to grab that out because we're going to need that soon. If you take the negative log of H+, which is the negative log of 1 exp negative 7, you're going to find out that the pH is 7. The easiest thing to do now is just take 14 minus 7 to get 7, and this is going to be a neutral solution. Okay, next we're going to look at the 0.1 molar HCl. We see that this is HCl. This is a strong acid. So I'm going to move this here so we could fill this in. This is a strong acid, so I'm going to write SA for strong acid here. And since it's an acid, I'm going to copy down this concentration in the H+. So it's 0.10 molar. Now that's the same thing as 10 to the minus 1st, okay, which is of course 1.0 10 to the minus 1st. So when you do the math, if you want to get the OH-, this would be 1.0 times 10 to the minus 13th. And then if you take the negative log of 0.1, take the negative log of this, or you could take the negative log of 1 exp negative 1, you're going to find out that the pH is 1. So this is a 1. Now let me pay attention to Sig Figs here. Interestingly, Sig Figs for a pH are past the decimal. So these are the Sig Figs. It doesn't count. Any number before the decimal does not count as Sig Figs. This is very tricky. So if we want to be consistent with our first example, this should say 7.00 and 7.00. Okay, now let's take 14 minus this to get the pOH, and that's going to be 13.00. And this is going to be an acid, which you can tell in several ways. One way you know it's an acid is because this is HCl. Another way you know is because the H+ concentration is larger than the OH- concentration. And then we also know because it has a low pH, you're an acid, or a high pOH. pOH gets a little confusing sometimes, so I personally don't really like to work in pOH. I just work in pH all the time, and if they ask me about pOH, I just simply subtract from 14 the pH and get the pOH. Let's go to the next one. The next one is also a strong acid, so we're going to copy down this molarity in the first column of H+, which is going to be 0.010, which is equal to 1.0 10 to the minus 2nd. I'm not going to be able to fit that with the Sig Figs, but hopefully you could see that. trying to write and it doesn't always do it when I want it. So let's fix that real quickly. This is a 0.010. Anyway, if you take 10 to the minus 14th over this, and by the way, when you plug in 10 to the minus 14th in your calculator, you really should write down 1. You don't need the Sig Figs with the calculator, so 1 is fine. 1 exp negative 14. That's the same thing on a graphing calculator as EE as well. Okay, the graphing calculator has the EE button. So 1 EE negative 14. This is really giving me some trouble here. Sorry, that's an EE. Or on a scientific calculator, it's going to be EXP. Great. Let's do this on a calculator. We're going to find out that the OH minus concentration is going to be 1.0 times 10 to the negative 12th. If you take the negative log of the H, you're going to find out that the pH is 2. Subtract from 14, and you're going to get a pOH of 12. And this is still going to be acidic. Now we switch gears when we get to NaOH. This is a base. It's a strong base. So when it's strong, you can just copy this number down, but this time for the OH minus. So this is going to be 0.10, which is the same, of course. I'll try to do Sig Figs here so you see it. 1.0, 10 to the minus first. So when you take 10 to the minus 14th over that, you're going to find out that this is 1.0 times 10 to the minus 13th. When you take the negative log of that, you're going to get 13. And subtract from 14, you get 1. And this, of course, is basic. Same thing can be said for the next one. This is also a strong base, NaOH, so we're going to copy this down in the base column. So 0.010, which equals, I'm not going to fit the Sig Figs here, so I'm just going to write 10 to the minus second, which means this one is 1.0 times 10 to the minus 12th. Take the negative log of this, and you're going to get 12.00 for the pH. Subtract from 14, you're going to get 2.00, and this is going to be, again, a base. So far, it's been pretty simple because you could see that the exponent of the 10 after the negative sign is always ending up being the pH value. And the same thing can be said about the OH value becoming the pOH. But what's going to happen is when you have a number that's not 1 times 10 to a power, you're going to get a pH that's going to be a decimal. So we're going to see that in this example. This is still a strong acid, and we're going to copy down this molarity for this acid in the H+, so that's going to be 0.25. Remember what 0.25 equals. It equals 2.5 times 10 to the minus first. This will help us out in a little bit. All right, now you're going to put this in your calculator. You're going to put 1 exp negative 14 divided by, you could put 0.25, or you could put 2.5 exp negative 1, and you're going to come up with something that may surprise you. Your answer on the calculator is going to be 4, let's write that in, 4.0 times 10 to the negative 14th. And you might say, well, hold on a second. This doesn't look right. Because you know that negative first and negative 14th are going to make negative 15th, and that's kind of contrary to what you were expecting when you saw this. But here's what you have to understand. Let me fix this so it looks like a 0 here. Here's what you have to understand. We're going to slide this up a little bit. If you were to do the math, you would see that this answer is actually right. Because even though 10 to the minus first times 10 to the minus 14th is 10 to the minus 15th, you know that 4 times 2.5 is 10 to the first. And you know, of course, that 10 to the first times 10 to the negative 15th gives you 10 to the minus 14th. So here's what you need to remember. Whenever you are multiplying H's and pH's that have numbers in front of the 10, the numbers in the front will always multiply to give you 10, and the exponents will always give you 10 to the minus 15th, and together it's going to equal 10 to the minus 14th. Okay, so big trick, want to watch out for that. Okay, let's finish this up. So we got to do the pH, which is the negative log of the H+, and that's going to come out to be 0.60, again with 2 Sig Figs. Subtract that from 14, and you're going to get 13.40, and this is an acid. Okay, we'll look at the next line. It's a base. It's a strong base, KOH. So when it's strong, we haven't learned what to do with weak yet, so they're all going to be strong for now. You're going to put that over here, so 0.025. And when you do the math for this, this is going to come out to be 4.0 times 10 to the minus 13th. And you take the negative log of the H, you're going to get 12.40. Subtract from 14, you get 1.60. And this is a base. Now, how do we work backwards if we know the pH? Well, if we know the pH is 4.75, that tells you right away it has to be an acid. Okay, we're going to pick a strong acid because, again, we haven't learned how to do the weak ones yet. And you could pick your favorite one. So while we're on the topic, you got to know your 6 strong acids: Hcl, Hibber, High, HNO3, HClO4, H2SO4. You got to know your strong bases, which is like the strong of bases. So we'll just pick your favorite one. Since we already did Hcl, let's do Hibber. So this is going to be HBr. We'll just pick any strong acid that only has one H. You can't pick sulfuric because it has 2. And you're going to figure out what is the H+ concentration. So you have to take 10. Let me scroll up a little bit here. You need to take 10 to the negative pH power. So you have to raise 10 to the negative 4.75. A couple ways to do this on the calculator. You could do 10 caret negative 4.5, or you could do shift log, which you'll see a 10 to the X button. So you could do shift log negative 4.75. Either way, you should get an answer 1.8 10 to the minus 5th. So write that in. 1.8 times 10 to the minus 5th molar. Now you're going to take 10 to the minus 14th, which is 1 exp negative 14, divided by that number to get 5.6 times 10 to the negative 10th. The POH, subtract 14 minus the pH, is 9.25. We are an acid in this case. And the molarity we're going to copy here is 1.8 10 to the minus 5th because that was the H+. So we had to copy down the H+ number since this was an acid. Okay, lastly, we're going to look at POH of 6.50. So with that, we realize that the pH, 14 minus 6.5, is 7.50, which makes it a base because it's above 7. So we're going to pick our favorite strong base. So instead of NaOH, let's just pick something else like LiOH. Make it interesting. We're going to take 10 to the negative 7.50, and we're going to get 3.2 10 to the minus 8th. And then we take 10 to the minus 14th over that, and we're going to get 3.2 times 10 to the minus 7th. And we copy down the molarity of the OH minus. So again, this is a 3.2. It's not that good over there. 3.2 10 to the negative 7th. And this is how we fill in the whole chart. Let's just go over a couple quick details here. When the number in front of the 10 is a 1, the pH comes out exact of the exponent. When there's a number in the front, like this 2.5, see the exponent here is 1 after the negative sign, and the pH is a little less than 1. Look at this one. There's a number in front. 13 is the exponent after the negative sign. Now this is a 12 point something. Here the exponent is 5. There's a 4 point something. Here the exponent is an 8. There's a 7 point something. So if there's a number in the front, the pH is always going to be the next whole number down from the exponent with some sort of decimal after it. Okay, let's just scroll up briefly here to wrap this page up. Acid dissociation constants are another special K that you're going to have for acids. And it's pretty simple. It follows the same procedure. Here's a weak acid. It just has H with something, like it could be HCN, HF, any non-strong acid. It's always going to have H with something. It breaks up into H plus and the anion. And it's only going to break up a little bit because it's weak. It doesn't want to break up a lot. So its K is going to be products over reactants, each raised to their power, which is going to look like this. And that's going to be its Ka value. And again, the Ka is going to be a small number because it's weak. It's a weak acid. So small Ka for weak acids. Whereas the strong acids, the K is like infinity. These are going to be much smaller. Okay? All of these are going to be small Ks. Now you could also write this, like I said before, instead of writing H+, you could write the hydronium ion, which means that this had to react with water, where the water takes the H from the acid to make hydronium and the conjugate. And it's going to be the exact same Ka, because remember that we're going to leave out the water. The water is not going to count. So you're going to leave this out of the equilibrium expression. And these two are really the same thing. Okay, so remember acids give you H's, but bases can take H's in these equilibria. So NH3 reacts with water to take an H and leave behind hydroxide. We're going to leave out the water again because the water is a liquid. So it's not going to appear in the Kb expression. So these are bases, and since they're weak bases, they're going to have very low Kb values. So these are going to be weak bases. They're not going to be the like of the stronger bases. On the next page, we'll start to take a look at each of these equilibria and figure out how to apply what we learned in chapter 13 with ice charts. Okay, so weak bases, weak acids.